Our discussion of pressure and how pressure varies with depth leads us to something called Archimedes Principle, which talks about buoyancy, or why things float in different fluids, or at least why they would feel lighter in these different fluids. So for this part, we'll consider a cube that is totally submerged in water, or it could be any other fluid, gas or liquid, and this would work the same way. And I just made some notes here that we'll say that the height of the the height of the cube is h, and that each side of this cube has an area A. Now, if we look at the forces acting on this, the force going kind of into the page on this front face is going to be balanced out by a force coming out of the page on this back face. And the force going to the left on the right face will be balanced by the force to the right acting on this left face. Those forces all balance each other out because they're all at the same depth. But we have this force downward that we'll call force down, good enough name for it, that's going to be different from this force upward because this bottom face of the cube is deeper than the top face, and we know that pressure, and therefore force, depend on the depth of the depth in the fluid that we're at. So force up we can write as the pressure, and we'll call that at the bottom face, times the area. So pressure times area gives us force. And then force down is going to be equal to the pressure at the top face times the area. Now pressure we know is going to be different at these two locations. So pressure at the bottom is going to be equal to, well, whatever the pressure at the top was plus the density of the fluid times gravity times the depth difference between the top and the bottom. So that'll be h. And then pressure at the top, we'll just say, is defined as pressure at the top. So now we can plug these in. We get F up is going to equal, just do the magnitude here, is going to equal the pressure at the top plus rho gravity h times A, and F down is going to equal the pressure at the top times A still. And then if we look at the two forces that don't balance each other here, our net force is going to be the force upward minus the force downward. And so that value is going to be, let's see, we'll have P top plus rho GH times A minus P top times A. And if I distribute that A, we've got P top times A plus rho GH A minus P top times A. So these two terms are just going to cancel, and we get rho times gravity times the height times the area. Now the height of this cube times the area of one of those faces, that's just equal to the volume of the cube. So I can rewrite that as rho times gravity times volume. And so this force, this net force that exists on this block, we call that the force of buoyancy. And it has a value equal to the density of the fluid times gravity times the volume of that object. Or we can think of that as being exactly equal to the weight of the water that is displaced by that object. And so that cube takes the place of some cube-shaped parcel of water that used to be in that position. And that cube has a volume of h times a, or just some v volume. And then if we looked at the water that used to occupy that space, it would have a density times the volume. Density times volume gets us the mass. Mass times gravity then would be equal just to weight. So the buoyancy force is exactly equal to the weight of the water or the weight of the fluid that's displaced by that object being there. Now this is a principle called Archimedes Principle, and the story goes that Archimedes developed this in trying to solve a problem for King Hero of Syracuse. The king was given this crown that was claimed to be pure gold, but he had some doubts, and he asked Archimedes, at least in the story, he asked Archimedes to determine, is this actually pure gold? And so Archimedes set about trying to figure this out by looking at the density of this crown and figuring out if it was had the same density as the established density for gold. So we're trying to figure out the density of this crown that's hanging in this water. We're given the density of the water. We have that the crown weighs 10.2 newtons, and right now, with it hanging in this tank full of water, it's hanging by this string, and there's 9.1 newtons of force acting on that string. So we need to figure out what the density for this crown is. Let's start with a free body diagram on this. So we have, let's see, the weight pulling it downward, the force of gravity, and then we've got the buoyancy force upward, and we've got tension upward. And so if I write out the net force equation, we'll have tension plus the buoyancy force minus the weight, or we could solve that as mass times gravity. We'll do that in a minute. And then since this crown is at equilibrium, it's just sitting there, acceleration is 0. So these three forces must then balance out. Now it might be useful for us to write out that the buoyancy force then is going to be equal to the weight minus the tension force. Now we have the weight given to us and we have the tension force, so then we can figure out that the force from buoyancy is equal to 10.2 minus 9.1 newtons. That would just be 1.1 newtons. So we have the buoyancy force, but we're looking for density. Now, what else do we know here? Well, we also know that the weight can be expressed as, and let's specify that this is the weight of the object, WO, can be expressed as the mass of the object times gravity, times that 9.8 meters per second squared. So the weight of the object then, if we're looking for the mass of the object and we're trying to find out density, we have this mass we can work with. We know that mass is exactly equal to the density of the object times the volume of the object times gravity. Or it might be useful then to express this as V naught, or not V naught, but VO, volume of the object, is equal to the weight of the object divided by the density of the object times G. If we go back to Archimedes' principle, the one that we developed just a minute ago, we found that the buoyancy force is equal to the density of the fluid times the volume of the object in there times gravity. So now we've got this expression for volume of the fluid. So the force of buoyancy is equal to the density of the fluid times the weight of the object over the density of the object times G in the denominator, and then times G up top. So we see our G's will cancel, and we get a buoyancy force that's equal to the density of the fluid divided by the density of the object times the weight of the object. And we know all of those variables. So here, the density of the object, I can write out, density of the object is equal to the density of the fluid divided by the buoyancy force times the weight of the object. So here that's going to be density of the fluid is 1,000 kilograms per cubic meter.
Good afternoon, staff. We'd like to get started right away at 1:15. So the sooner we get everyone down there, the sooner we get started. Thank you.
Okay, density of the fluid times the weight of the object, the crown, was 10.2 newtons, times the force of buoyancy, which we calculated at 1.1 newtons. Okay, so the density for the object then is 102,000 divided by 1.1, and we get about 92,700 kilograms per cubic meter. So then we would just compare that to the established value of the density for gold, which is 17,000 kilograms per cubic meter, and we can see that this number is definitely pretty far off from that value. So we've got we've got a gold crown that isn't really gold.